Today we are going to chapter 5, the first part of chapter 5 of work method. First, let me make some review on what we have learned about. As you already know, in plastic analysis and design, three conditions should be satisfied. The first condition is equilibrium condition. The second condition is mechanism. And the third one is moment. Moment should be smaller than MP. Plastic bending capacity of a section. In equilibrium method, for the small structure, we start with equilibrium equation and the moment check, and then we do the mechanism check. So for the small structure, we have three steps, right? You already learned. For the large structure, we start with equilibrium and assume mechanism. Okay, we start with equilibrium and assume mechanism, and then we do the moment check. The procedure for the large structure is a little bit changed. So beyond this procedure, we have 8 steps, right? We already mentioned about this. For work method that we are going to continue today, I already introduced about the concept of work method, right? But today we are going to study the further application of work method in plastic analysis. And as you know, in work method, first we assume the mechanism, and then beyond the assumed mechanism, we write the equilibrium equation. That is work equation. Okay, and then we do a moment check. And that is what we are going to continue with work method today. And one more thing that I already mentioned is work equation. In chapter 3, I already mentioned the work equation is WE equal to WY. Here, WE is external work, and here is internal work. In terms of equilibrium set and displacement set, the left-hand side part is external work, and the right-hand side part is internal work. And P and M is equilibrium set. Theta and theta is displacement set. And moment check. If the moment check is satisfied, then we have exact solution. But if the moment check is not satisfied, then in analysis we have upper bound solution, and in design we have lower bound solution. Okay, so I remind you what I have already mentioned in chapter 3. That is very basic concept. Let me give you an example to illustrate the application of work method with analysis problem. Let's consider a ball fixed and beam with concentrated load. As you can see here, It is very simple example to remind you the application, a simple application of work method. This is assume mechanism. We assume mechanism at both ends and at the middle. Okay. Then with this mechanism, we have the equilibrium set. No, displacement set. Okay. Theta, theta, and this angle is 2 theta. And this displacement is L over 2 multiplied by theta. Okay. Half of L multiplied by theta. And with the assumed mechanism, we have here is MP and MP and MP. Then we have equilibrium set MP, 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 and P. Write down the work equation. External work equal to internal work. What is external work? External work equal to P multiplied by displacement here. Okay, equal to L over 2 multiplied by theta. And internal work. Internal work equal to MP multiplied by theta and MP multiplied by 2 theta and MP multiplied by theta. Then we have MP theta 2 theta theta equal to 4 MP theta. Then external work equal to internal work. Then we have P equal to 8 MP over L. Firstly, we don't know this is correct solution or not. So in general, for analysis, we have upper bound solution. Pu equal to 8 MPL. But if we do the moment check, and M equal to MP, equal to MP, and equal to MP, then all M is smaller than or equal to MP. Then the equilibrium and moment check is satisfied. It means this value is correct solution. Okay, correct solution. MPC. Because our assumption is correct assumption mechanism. Okay. Okay, so let's move to another example. Now we are going to consider a three-span continuous beam, as you can see here. Beam has three span, AC and CE and EG. The distance of the first span is 2L, and the second is CE is L, and EG is 1.5 L. The load is at the middle of each span. The value is P and P. So the location of load is B and D and F. Okay. This is analysis problems. It means the beam has MP. Okay, the beam has the same section, MP, and our task is to determine PU. So that's why it is analysis problems. Now we assume mechanism. Okay. This is assume mechanism. Our first assume mechanism. So we assume it's the plastic hinge occur at B and C. Then we have three hinge, two plastic hinge and the original hinge. With this assumed mechanism, we have external work equal to P multiplied by L theta. And this is external work. How about internal work? Internal work equal to P MP multiplied by theta here and 2 theta here. Then we have 3 theta and 3 theta MP. Theta and 2 theta MP. So very simple. We have external work equal to internal work. Then we have P equal to 3 MP over L. Okay, 3 MP over L. This is solution corresponding to this assumed mechanism. Okay, so we don't know if this is correct solution or not, but it is assumed mechanism. And we have this solution. And we are going to check in next step. Okay, so remember, this is assumed mechanism and this is solution. P equals 3 MP over L. Okay. Moment check. To do the moment check, firstly, we have to determine the number of indeterminacy of the structure at collapse, I. In another word, I is degree of indeterminacy. I equal to x minus m plus 1. I equal to x minus m and plus 1. Here I is the number of indeterminacy of the structure at collapse. And x is the number of redundancy in original structure. Okay, x is number of redundancy of in original structure. And m, what is m? M is number of plastic hinge necessary to develop the mechanism. Again, M is number of plastic hinge necessary to develop the mechanism. Okay, so let's see. Back to the previous example, 3-span continuous beam. So with this structure, what is X? Here, X is number of redundancy of original structure. How many redundancy of this structure? 1 and 2. Okay, 1 and 2, 1 and 2. So we have two redundancy of the original structure. And M is a number of plastic hinge necessary to develop the mechanism. So, how many plastic hinge which necessary to develop the mechanism? Here, 2, right? M equal to 2, 1 and 2. So, we have X equal to 2 because 2 redundant. And M equal to 2 because of requirement, number of requirement plastic hinge. Then we have I equal to 2 minus 2 and plus 1, this equation. Then it's equal to 1. So the degree of indeterminacy equal to 1, greater than 0, or greater than 0, okay? It is 1. So I equal to 1. So again, X is the number of redundancy of original structure. And here we have 1 and 2, two redundants, okay? And 2 require plastic hinge. 2 require plastic hinge. Then we have I equal to 2 minus 2 and plus 1. And it is 1. It means the degree of indeterminacy equal to 1. 3-span continuous beam. For determinate structure, simple plastic equation or waterwork equation can be used. Okay, for determinate structure, simple static equation or waterwork equation can be used. However, for indeterminate structure, both simple plastic and waterwork equations may be used. Okay. So back to this example. This is indeterminate structure. Right? We have the degree of indeterminacy equal to 1. So we use waterwork. With waterwork, because I equal to 1, then we try ME as redundance. As you know here, we assume the plastic hinge at B and C. Then here we have MP. Okay, here MP, and here is MP. So we already have MP and MP. Here is MP, and here already MP, because of our assumed mechanism. Okay, so how many unknown? 3 unknown, right? This one, M at D is unknown, and M at E is unknown, and M at F, moment at F, is unknown. So we can plot the moment diagram of the beam like this, but we already know M at B and M at C is MP based on our assumption of mechanism. 3 unknown is MD and ME and MF. 3 unknown. Now we try with ME at redundant. So we assume ME is null. Okay, we assume ME is null. Then now we have to determine MD and MF as a function of MP and ME. Okay, can you follow me? So may I explain one more time? We assume mechanism. Beyond the assumed mechanism, we have MP and MP. Okay, MP and MP. And we have it is analysis problem, so we already determined P is 3 times of MP over L Is this right? In the previous step. Then if we know the MP, then we have P. If we can calculate M at any section is a function of MP, then here we have P, then we can calculate F as a function of P or as a function of MP. Doesn't matter. So back to here, we have MP and we have MP. And we have three unknown. Okay, three unknown. Because this I, in this case I equal to 1, as a result of the previous step, then we try with ME as redundant. The degree of the indeterminacy is 1, then we assume ME. Then now we have two unknown, D, M at D and N at F. Then we have to determine M at D and M at F as function of MP and ME. Okay. MD and MF is function of ME and MP. We already have MP and we assume the redundant is ME. Then next step, we are going to determine MD and MF as a function of ME and MP. ME and MP. Okay, so don't be confused. Try to understand and try to follow me. I hope they can follow me. So next step, we determine MD and MF as a function of ME and MP and do the moment check with them.